Okay, welcome to this week's academic training, which will be on nuclear fusion, as you've seen, in particular the ITER project. So we have 4 lectures this week. The first 2 lectures will be given by David Campbell, which we have the pleasure of having here with us, who then these lectures will be mostly on the physics which is involved in nuclear fusion and what is needed for that. And then the next 2 lectures will be given on the technologies from ITER and more details on that. So as for the speaker, since he's talking on the physics, we are very lucky actually to have David Campbell here with us, who's the leader of the physics program of the ITER project. And he himself has already more years than he wants to remember probably of experience in fusion, among others in the JET project, and before that already working for 10 years in preparation for the ITER project in Garching, as far as understood. And since 4 years now, since the lab got into construction, he has been at ITER itself in Cadarache. So, David, thanks for coming, and it's all yours.
Okay, thanks very much, Alda. Good morning, ladies and gentlemen. It's a real pleasure to be here and to CERN. Last time I was here for any time was 30 years ago when I was a PhD student, and I knew another PhD student who worked here, and he gave me a tour, and that's the last time I had to look around. So it's nice to have the opportunity to come back, and this time to be talking about fusion, and in particular about the ITER project. What I'm going to be talking about, as Albert said, are the physics aspects of fusion in general and of the ITER project in particular. Now we have to see if this will actually.
That does not go forward.
Maybe it's just, okay. It did before.
This is also not compatible with yours, I'm afraid. So better.
Okay, I'll just use the
classical.
The normal way, as long as it works. Let's see if we can start over again. Could be something about the way it could be something about the way the keyboard's set up.
Can you have yours again?
Yep.
I'll put it on mine. So there are some technical difficulties with
alternative is just to do a. Sorry for this. Hiatus. Let's see. suppose that it must have got confused by the USB stick.
Is that the same as I have? No, I have a different one.
Okay. Just going to give it one more try.
You can try it there and see if it advances on your computer.
Okay. Great. Well, we'll do it that way then.
Yeah.
Okay.
But then I have no emails.
Doesn't seem to want to work now. I'll have to.
So you can even use this thing now.
Okay, so that actually works. Okay.
All right.
Appreciate it.
Okay, take two.
Okay, so we'll try once more. Sorry for the technical hiatus. So this is the first of a series of 4 lectures dealing with fusion in the context of the ITER project. I'm going to give the first 2 dealing with physics aspects of fusion, and then my colleague Gunter Januszczyk will give the 3rd and 4th lectures dealing with technology aspects of the ITER project, and then looking forward to the technology for a power plant. So today I'm going to talk about some fairly basic aspects of plasma physics for fusion plasmas. I hope you won't find the level too low. It's my experience generally that although the physics concepts, the basic physics we use in fusion are relatively simple, the field is bedevilled with so much jargon and some of the parameters are so unusual that unless you actually take the time to define them in advance, you find that people don't actually understand the language you're using. So today I want to give a lead-in to basic concepts in fusion, some of the basic physics parameters, so that tomorrow I can spend more time talking about the details of the sorts of fusion physics that we're looking forward to doing in ITER. So what I'm going to talk about today is to give a brief introduction to thermonuclear fusion. I'm mainly talking here about magnetic confinement fusion. It is a magnetic confinement device, but I'll say something briefly about inertial confinement, because inertial confinement has also reached quite an interesting time in its development. I just want to take a couple of slides to contrast the sorts of concepts and parameters we work with in magnetic fusion and inertial fusion. And then I'll talk about basic physics aspects of the tokamak and explain to you what a tokamak is. Then I'll give some introduction to basic plasma physics for magnetic confinement, and then I'll round off this lecture with a brief introduction to the ITER project. And again, my colleague Gunter Januszczyk will give you a lot more details on the technology of ITER. So this, on your right-hand side here, is what the ITER tokamak will look like by about 2019. I just want to give you a very brief introduction here to set the scene for the rest of the lecture. It's a large device. It's about this, what you see here is the tokamak itself, a donut-shaped tokamak embedded in a structure which is the cryostat. And the cryostat's about 30 meters across, 30 meters in diameter, and about 30 meters high. It gives you an idea of the scale. The ITER project is a project which is made up of 7 partners representing basically the world's major fusion research communities, but also the world's major economic communities. It's designed to produce 500 megawatts of fusion power with a fusion amplification factor of about 10, and I'll explain how we define that fusion amplification factor, for extended periods of time, several hundred seconds. We're spending about 10 years constructing it. There'll then be principal 20 years of operation to exploit it, 5 years of deactivation, and finally decommissioning. And so these lectures over the next 4 days will explain the background to ITER, the physics and technology details, and how ITER fits into the overall context of fusion energy development. Let me just summarize what we're trying to do so that, oops. Looks like I pressed the wrong button here.
Yeah. Not to worry. Maybe I should sit here or something.
Yeah. Technology can be a dangerous thing. Okay. Once more. Thanks, Abel. Okay, so the basic scalar device is shown here on the left-hand side. The major radius of the donut is 6.2 meters, and the minor radius is 2 meters, and I'll explain in more detail what that means. Total volume of plasma is about 830 cubic meters. We run, or will run, plasma current of about 15 megaamperes, and I'll explain to you in the course of these 2 lectures why we need such a large plasma current. There's a main toroidal field of 5.3 Tesla on axis. Target parameters for the plasma, for the DT burn, are a density of about 10 to the 20th particles per cubic meter, a peak temperature of about 200 million Kelvin. That should produce a fusion power of about 500 megawatts, and our aim is to sustain that for periods of 300 to 500 seconds, although there's a more advanced mode of operation and longer term, what we call steady state operation, for periods of up to 3,000 seconds. And in our context, steady state is meant to form the basis for genuine operation of a steady state power plant. Now, the basic principles of what we're doing is this is now a cross-section through half the donut, shows ITER with a plasma in it, and this shows the cross-section of the plasma showing magnetic flux surfaces. And basically, it's in some senses a large oven. What we do is we feed in deuterium and tritium fuel. This is ionized in the plasma. It reacts. The reaction products are an alpha particle at 3.5 MeV. This is trapped in the plasma and heats the plasma. There's also a 14 MeV neutron which escapes from the plasma. Around the outside of the plasma, between the plasma and the vacuum vessel and the superconducting coils, there's what we call a blanket. In ITER, this is simply a neutron absorber to protect the superconducting coils. In a power plant, this would be much more sophisticated. The blanket would contain lithium to breed tritium, and that's how we get the tritium for a fusion reactor. In addition, it would operate at high temperature, and the high temperature coolant would then be taken off to drive an electrical generator. At the bottom here we have a structure called the diverter, and I'll describe what the diverter does in more detail tomorrow. But basically, it sucks the heat and the particles out of the plasma, and afterwards they're pumped off using cryopumps. The main waste product is the helium that's produced in the reactions. There's a lot of deuterium and tritium left over, and there are various other minor impurities. So that's the basic idea of what we're trying to achieve. And so what I want to discuss over these next 2 lectures, in some senses, is why it's so difficult to achieve that and what we're doing to achieve it. So let me turn now to give you some background details about thermonuclear fusion. I just want to take one slide to summarize why we're interested in fusion as an energy concept, assuming that we can solve the physics and technology problems involved in building a fusion reactor. It's well known, I think, that we're expecting the world's population to grow during the remainder of the century, and that energy consumption will perhaps double, perhaps triple, perhaps quadruple during that century, depending on how far countries such as India, China, and the rest of the developing world develops and raise their standard of living. So there's clearly going to be a need for more energy during the course of this century. Fusion we see, if we can solve the technical problems, as an attractive option The fuel is abundant and it's distributed worldwide. Deuterium we extract from seawater, and there are sufficient supplies in seawater for millions of years of power production. Tritium, since it's radioactive with a half-life of just over 12 years, you don't find lying around on Earth. We would breed that in a reactor, as I've said, from lithium in the blanket, and there are sufficient ore supplies of lithium for thousands of years of power production, and if we want to extract lithium from seawater, for millions of years. So there's a lot of fuel, and nobody in particular owns the fuel. Safety aspects of fusion are pretty positive. There's no risk of major accidents. The reactor itself contains fuel for only a few minutes of burn, and in fact, if you were to stop feeding more fuel in, the burn wouldn't actually last for as much as a minute, because basically the reaction would be poisoned by the reaction products. As far as waste is concerned, we're developing materials so that there should be low radiotoxicity after about 100 years, and there's no CO2 production. So this basically is our argument in favor of fusion energy. So let's look at the fundamental principle. Well, I think probably everyone here understands the fundamental principle. We're basically converting mass into energy. We're using the fact that there's an excess of binding energy at the low end of the atomic mass scale, just as there is at the high end of the atomic mass scale. In the deuterium-tritium reaction, which we are planning to use, and I'll explain in a moment why we favor deuterium-tritium, the mass loss in DT reactions is only about 0.4%. As you can see from this graph, the energy gain per unit mass is greater for fusion than for fission, although the energy gain per reaction for uranium fission is considerably larger than for DT fusion. Nevertheless, the energy density that's available in fusion fuel means that a gram of DT fusion fuel is worth roughly 2,000 barrels of oil. So it's a very high energy density. The essential fusion reaction that we're interested in is the deuterium-tritium reaction. This, as I described previously, produces an alpha particle with an energy of 3.5 MeV, and being charged, this is trapped in the plasma and heats the plasma. The remainder of the energy is carried off by the neutron, which is absorbed in the blanket surrounding the plasma, and would be used to heat the coolant and generate electricity. And this is the simplest reaction to achieve under terrestrial conditions. This shows a graph on the right-hand side of the reactivity for various candidate reactions as a function of the ion temperature in the plasma. And you can see here that the lower end of the temperature scale, the DT reaction has a factor of about 100 advantage over other simple reactions such as DD or D helium-3. And this means that the confinement qualities of the plasma are significantly easier to achieve for DT fusion than for DD or D helium-3 fusion. There's a couple of other important nuclear reactions for the DT fusion cycle, and that's the reaction of lithium with neutrons. There are two possible reactions, one with lithium-6, one with lithium-7. Lithium-6 reaction is actually exothermic and can be used in the blanket to generate yet more power. And it's these reactions in which we rely to breed the tritium, which is then fed back into the reactor. So looking in more detail at fusion power production, we need, as you saw in the previous graph, ion temperatures of at least 10 kilovolts in order to get significant fusion power output from a plasma. The nuclei must overcome the Coulomb barrier to approach close enough to fuse. In fact, if you were simply trying to get over the Coulomb barrier, which is about 0.4 MeV, you'd need a temperature around 300 keV in order to achieve thermonuclear fusion. That is a fusion in a thermal environment. But the reaction rate turns out is dominated by a small population of high-energy nuclei, which react by quantum tunneling. For example, for 100 keV nuclei, the tunneling probability is about 3.2 times 10 to the minus 2. And it's this phenomenon that actually makes it possible to achieve significant fusion power output at temperatures as low as 10 keV, or 100 million degrees. The fusion power density for an optimal 50-50 DT mixture is given by this expression. It depends on the density of the plasma squared. It has the reactivity, sigma V here, and this is the fusion the energy associated with fusion reaction, 17.6 MeV. You can express this in this form, which is quite a nice way to express it. This is then the plasma pressure. It turns out that for temperatures we're interested in, around 100 million degrees, this here is approximately proportional to T squared. So you can then see that the fusion power is basically just scaling with the plasma pressure squared. So to give you an example for a possible fusion reactor where the plasma pressure might be 10 atmosphere, this would give you a central fusion power density of about 7.5 megawatts per meter cubed, that should be, my apologies. That's significantly higher than you get in a coal-fired plant, although still lower than you would have in a light water reactor. Now, how do you figure out just what the plasma parameters have to be in order to get a net fusion power output from a DT plasma? It's a fairly simple analysis you can run through. Obviously, for net power gain, you have to, the heating power that comes out of the reaction must exceed any heating power you put in to get the temperature up to 10 kilovolts. And I'll go into more detail tomorrow to tell you about how we actually go about getting the temperature up to 10 kilovolts. There are various loss processes in a reactor. There's Bremsstrahlung radiation, there's synchrotron radiation, there's normal thermal conduction, there's convection processes. And the fusion power that's being produced by the DT reactions, in particular the energy associated with the alpha particles, must balance that, those loss processes. We define a parameter conventionally, which is one of the most important parameters in fusion research, tau E, the energy confinement time. And this is simply defined as the ratio of the thermal energy in the plasma to the loss power. So you can think of it fairly simply by analogy with a bath of water. If you have a bath of water, you pull the plug out, the water energy confinement time is the rate at which the water is flowing down the plug hole. And so the energy confinement time in a fusion plasma is a similar concept. One can then write the overall power balance in this form. This is the term with the energy confinement time now. This is the fusion power. So this is the loss power, basically. This is the fusion power being produced by the reactions. And in this equation, the heating power is actually the external heating power. So it's the heating power that's coming in from the outside without ignoring the alpha particle power, which is expressed in this term here. And what we would ideally like to get in a fusion power plant is a situation where this heating power, the external heating power, is zero. And in that case, you have to satisfy this criterion. This is the criterion we call ignition, where you turn off all the external heating powers and the power produced by the DT reactions in the plasma support the loss processes and keep the plasma hot. So this condition, ignition, implies n tau is greater than 12 over sigma v kT over E alpha. And it's this condition, we then define a parameter, which is Q, the fusion power gain. And the fusion power gain is simply the fusion power divided by the heating power. Now, obviously, when you get to ignition, the external heating power is zero, and so Q goes to infinity. And this has always been the holy grail of magnetic fusion research, that you could produce a plasma where the DT reactions would be self-powering. You could turn off all the external heating. Now, when we actually look at the realistic design of a power plant, it turns out that this is rather idealized. It's actually unnecessary. We don't need an infinite Q. We need a Q probably of order 30 in order to build a power plant that can produce electricity economically. But when I came into fusion, going on for 30 years ago, and JET was just starting up, all of the people I spoke to when I first came to JET said, you know, JET will be the first machine that produces any DT fusion power, which it did in the 90s. It won't get anywhere near ignition, but the next machine must ignite. It was thought, it was always the goal of the fusion program that we would build a machine that would achieve ignition. Well, in fact, in the 30 years I've been in fusion, it's come to be accepted that that's an unnecessarily difficult target, that what we really want to do is to build a fusion power plant, and what we need to do is to achieve a large but finite gain, and that gain's around 30. So following on this line of analysis, you find that in order to achieve this condition of ignition, you have to satisfy this simple inequality here. The average density times the energy confinement time has to be greater than 1.5 times 10 to the 20th per meter cubed second. This comes out of this graph here, which shows how n tau varies as a function of the temperature in the plasma. There's a minimum in this curve in the region of 20 to 30 kilovolts, which corresponds to that. And so it's into this region that you have to get the plasma if you want to achieve ignition. And this criterion, or something very similar to it, it wasn't exactly numerically the same, was derived by John Lawson in the 1950s, and it's possibly the most famous equation in magnetic fusion research. It's known as the Lawson criterion. We tend not to use the Lawson criterion in magnetic fusion now. You take this analysis a step further, and you can define another parameter. Rather than the fusion power amplification factor, which goes up to infinity as you're approaching ignition, we tend to define an ignition margin, CDT, in terms of the fusion triple product. This is the ion density times the ion temperature times the energy confinement time. Do some simple algebra, you can show that the ignition margin is actually QDT over Q plus 5. So this eliminates the infinity. It's just the ratio of the alpha power going into the plasma to the loss power. And so when this is exactly balanced, the ignition margin is 1. And you can derive, by making second assumptions about the plasma profile shapes, you can derive a simple equation, a simple expression for CDT, which is this. It's this 2 times 10 to the minus 22, the DT density, central DT density in the plasma, the central DT temperature, the energy confinement time. And here we typically, for most of our work, we work with temperatures in kilovolts. That's roughly one EV is roughly 11,600 Kelvin. And so this gives us a simple way of characterizing, it's a quality factor which gives us a simple way of characterizing how good the fusion performance of a plasma is. So, and what are the parameters we need to achieve in order to achieve significant fusion power? Well, the target temperatures, as I mentioned, are in the region of 1 to 200 million Kelvin, 10 to 20 keV. That's about 10 times the temperature of the sun's core. The reason the temperature has to be so high is that the density is so low. It's about 10 to the 20th particles per cubic meter, which is about a millionth of the atmospheric particle density. The energy confinement time we aim for in a machine like ITER is a few seconds. And one of the things I'll be discussing tomorrow is how this energy confinement time depends on the plasma parameters. Basically, what we've discovered in the course of our experimentation is that you can increase the energy confinement time by increasing the plasma current and increasing the radius of the device. It actually goes as the radius squared. And the energy confinement time I should distinguish from the actual plasma pulse length. We've developed our capabilities in controlling plasmas to the point where we can actually produce plasmas and maintain them for hundreds of seconds. In principle, if the magnets would take it, we could control them for thousands of seconds. And the plasma pulse duration we aim for in ITER is typically of order 1,000 seconds. The energy confinement time, as I said, is this, as I explained, is this parameter which characterizes the efficiency of energy containment in the plasma. So if you put those numbers together, you get this fusion power triple product, n tau t. Present devices such as the JET device, which is situated at Cullum in the UK, large European experiment, has achieved Q just under 1. It has actually achieved Q of about 0.6. ITER is designed to achieve a Q of at least 10. And in a power plant, we aim to achieve what we call controlled ignition with a Q of around 30. What we've actually achieved in the course of the history of fusion research is illustrated here. This shows this parameter, the fusion triple product, on the vertical axis against the central ion temperature in the plasma on the horizontal. There's a series of points which have been taken from a large range of fusion experiments over the last 40 to 50 years, starting with the T3 experiment, which was the Russian Tokamak experiment, which really kicked off the development of Tokamak fusion, going up to the large experiments of the most recent generation JET, the American equivalent TFTR, and the Japanese equivalent JT60U. The points shown in red here were points that were experiments carried out in DT plasmas in the late 1990s. And you can see from this graph that we're getting into the region where Q equals 1. We've still got, in terms of Q, we've got a factor of about 10 to go in ITER. In terms of this triple product, N tau T, we've got about a factor of 5 to 6 to go in ITER. Let me just turn very briefly now and say something about inertial confinement. I think it's interesting to comment on this because the inertial confinement community has also been making rapid progress over the last 20 or 30 years, and we're actually expecting in the next couple of years that the National Ignition Facility, which is the major laser-based facility at Livermore in the US, may well achieve what's called ignition in the inertial confinement world. I don't want to get into all the technical details of inertial confinement. It's a very wide-range nuclear-like magnetic confinement. There are different forms of drivers. There's laser drivers, there's heavy ion drivers, there are Z-pinch drivers. There are different forms of targets. There's simple spherical targets. There are what are called whole-arm targets, in which a small capsule is embedded inside a cylindrical rod which generates X-rays when hit by a laser. But I just want to say something very brief about this. This shows the type of ignition diagram that's used in inertial confinement. On the left-hand side here, you have the target gain. So you take a target, you hit it with a driver of some sort, let's say a laser. You put a certain amount of power in, you get a certain amount of power out, and that's the target gain. It's against the driver energy. And the experimentation that they've done over the years in inertial confinement gives them reason to expect that with a driver energy of 1 to 2 megajoules in the National Ignition device, they should be able to achieve a target gain. So for 1 to 2 megajoules of laser energy in, they're expecting to get something like 10 to 20 megajoules out. There's two interesting points to make about this. One is that the definition of ignition in magnetic fusion and the definition of ignition in inertial fusion are rather different. As I've shown in the first part of the lecture, in magnetic fusion, the ignition criterion is based on a power balance in the plasma, and we want to get more power out than we're putting in. In ICF, it's rather different because they don't have a steady state system. They have a pulse system. They inject a certain amount of energy in, they get a certain amount of energy out. And the key criterion there is for ignition is the burn propagation in this target that generates so they try to get the target hot enough to start burning DT, and then they're looking for that burn to propagate through the plasma that's produced. And so it gives rather different numbers. So the magnetic fusion criterion, as I said, is N tau T is around 5 times 10 to the 21. It's interesting, this gives a fuel burnout fraction of a few percent, so it means you've got to keep cycling the fuel through the Tokamak to burn it up, because at any time you're only burning up at a rate of a few percent. The ignition criterion is based on the idea that to get significant energy out of the target, you need a burnout fraction of about 30%. And this then gives them a criterion based on the density that they reach in the compressed capsule times the radius of the compressed capsule, which is about 2 kilograms per meter squared. So these are quite different considerations. And therefore, this is why to get a high Q in a magnetic fusion device, you need to produce hundreds of megawatts, whereas in ignition, in inertial confinement fusion, they think they can achieve ignition by simply producing 10 or 20 megajoules of energy. It's interesting to compare some of the key parameters of ITER and the plasma in ITER and in the National Ignition Facility compressed capsule. You can see that there are many orders of magnitude. You're working in quite a different region of plasma physics. The ion density is different by about 11 orders of magnitude, as is the density, obviously the mass density. But the only thing that's common to the two is that you've got to achieve a temperature of around 10 keV in order to produce significant fusion energy. So that's just to give you an idea of where magnetic fusion and inertial fusion stand. So let me go on to describe you a little more about the Tokamak. The Tokamak is basically a magnetic confinement system. It's based on the Lorentz force. What we do is we take a toroidal configuration. We impose magnetic fields around the torus. That causes the charged particles in the plasma to spiral around the torus. And this means that the charged particles, which are then spiraling around the torus, are free to go around the torus, but they diffuse only very slowly across the field. A lot of the initial magnetic confinement experiments were carried out in linear machines, and the problem, of course, is that you confine the plasma in the transverse direction, but in the longitudinal direction, you lose the plasma at the ends of the device. And this is what gave rise to toroidal confinement. There are different forms of magnetic configuration you can establish in a torus, and I'll show you a few of those in a moment. But the special version of this is called the Tokamak, which is what we work with. This is an abbreviation for toroidal chamber and magnetic coil in Russian. The Tokamak was first developed in Russia, in the old Soviet Union, in fact, in the early 1950s. But it wasn't until the late 1960s that the T3 device started to achieve interesting results. It achieved a temperature of 1 keV, which was then unheard of at that stage of fusion energy research. And that's really what transformed the field. So what does the Tokamak look like more realistically? Well, this shows a sort of cartoon of a Tokamak illustrating the main elements of it. You have some external coils for producing a strong toroidal field a long way around the torus. You have a transformer, which is represented here by an iron core with a central solenoid in the middle of the device. If you change the current through this central solenoid, the effect is to drive a changing flux through the solenoid, which also drives a changing flux through the region of the torus. This produces an electric field. It produces an electrical breakdown and starts to drive a current through the plasma, which then gradually expands and fills the torus. This then produces, the current then produces what's called a poloidal field, which is a field the short way around the torus. And so the combination of this strong field that runs the long way around the torus and the poloidal field running the short way around the torus produces helical magnetic field lines. So the magnetic field lines spiral around the torus in helices. And it's that mode of production of the magnetic field and that type of magnetic field that makes the Tokamak. In addition, you have a few extra coils around the outside of the device in order to help you control the device and to shape the device. Now, this is the basic principle of a Tokamak. This shows the largest existing Tokamak. It's the JET device at Cullum. It's about half the dimension of ITER, and in fact, JET does have a very large and very prominent iron core. We tend not to build Tokamaks with iron cores anymore because we've got a lot smarter computational skills. We've got a lot better, computing powers got a lot better. We're able to design the sophisticated magnetic field configurations and toroidal geometry that we need to confine the plasma properly. We used to use the iron cores to help us shape the magnetic field, but we don't have to do that anymore, and you don't find modern Tokamaks with iron cores. But you can see the scale of the JET device. It's the iron core is about 15 meters across and about 12 meters high. JET itself has a major and minor radius of 3 meters and 1 meter. It contains a plasma volume of about 100 cubic meters. So ITER is a doubling of the linear dimension, a factor of 10 in the volume of the plasma. It has a toroidal field of 3.4 Tesla and a plasma current. A maximum plasma current has been demonstrated of 7 megaamperes. And in DT experiments in '97, they reached a peak fusion power of 16 megawatts for about a second, producing a peak QDT of about 0.6. This shows what the inside of JET looks like. This shows it during a shutdown. There are various elements on the inside of the torus. These are largely tiles to protect the metal walls of the vessel. That's another thing I'll talk about tomorrow. On the right hand, this gives you just an idea of the scale of the torus itself. On the right hand side, you see the view when they're operating a plasma. What you see here actually most prominently is the cold part of the plasma where it's interacting with the wall, where the temperature is probably down around 100 eV or so. The hot part in the center radiates in the X-ray and UV region, and so you can't see that. So, going on in a little more detail about a Tokamak, as I said, the Tokamak field lines spiral around the torus, as shown in this top diagram here. we define the toroidal field as b phi and the poloidal field as b theta. I've been using this concept, the major radius, which is the distance from the axis of the torus to the axis of the plasma, and the minor radius A is the distance from the axis of the plasma to the edge of the plasma. Now, the reason that we need this spiraling field line geometry is that if you only have a strong toroidal field around the torus, you find that because there is curvature and a gradient in the toroidal field, that the ions and electrons drift vertically in opposite directions. This then very rapidly produces a very strong electric field, which drives the plasma out of the torus, and you have no confinement. So the additional poloidal field, which you impose through the plasma current, which creates those helical paths around the torus, allows the particles which are drifting in the toroidal field essentially to run around to the bottom of the torus again, and this cancels out these electric fields. So it gives you good plasma confinement. There's an important number, which is the winding number of the helix. This is an important stability parameter. It's referred to as Q. Here I define Q in a very simple way. This is what's called the cylindrical Q. At the edge of the tokamak, it's simply the minor radius times the toroidal field on axis divided by the major radius times the poloidal field at the edge. Another parameter which will come up again is this R over A, is the aspect ratio of the device. And so to give you an idea, in jet, the relative strengths of the toroidal and poloidal fields are as shown here. On axis, of course, the poloidal field 0. It's a factor of several. The toroidal field is a factor of several above the poloidal field at the edge of the plasma. The significant feature of the toroidal field is that in a torus it has a 1 over R dependence. And this becomes important. There are different toroidal magnetic configurations. There's the tokamak that I've just described with a strong toroidal field and a strong current. There's another device called the reverse field pinch, which is a weak toroidal field and a strong plasma current, so that the ratio of the toroidal and poloidal fields are closer to unity, although they vary across the torus. This is a device, to put it simply, that has problems with plasma stability because the toroidal field isn't strong enough, basically. And there's another device called the Stellarator, which is a strong toroidal field and no plasma current at all. And you then ask, how does it get the poloidal field? Well, it gets the poloidal field by special external windings, which produce the poloidal field totally externally. Of these configurations, the tokamak has progressed most rapidly and is ready for the thermonuclear step. But the Stellarator has certain interesting features, and so there's still considerable work going on in the Stellarator area. This shows two largest Stellarators which are around at the moment. On the right-hand side is the large helical device in Japan. These are fairly substantial devices. You see a typical diameter of around 10 meters. Large helical device in Japan has already been operating for a number of years. It's referred to as the heliotron because the external windings are actually helical windings which wind around the torus and help to produce this helical field. On the left-hand side is the Wendelstein 7X Stellarator, which is under construction in Germany, will be operational in the middle of this decade. It's what's referred to as a modular Stellarator because the way in which it produces the helical field is through these rather complicated external coils. So instead of having simple cylindrical, for want of a better word, toroidal coils, you take the toroidal coil and you twist it in the toroidal direction. And so you end up with a series of very complicated coils which ends up producing your helical field. The reason the Stellarator remains interesting is because there's no current to drive, you don't need the transformer action, and because you don't need the transformer action, you have the possibility ab initio of steady-state operation. One of our bugbears in the tokamak is we want to turn the tokamak into a steady-state device, and as long as you have a transformer action, that's a challenge, and I'll talk about that tomorrow. Overall, the Stellarator energy confinement is similar to that in equivalent current tokamaks. It took them a while to catch up to tokamaks just because the success of the T3 experiment in the Soviet Union created a rush towards the tokamak configuration, and it's easier to build a tokamak than a Stellarator, as you might imagine. But in fact, the energy confinement performance is about the same. Looking in more detail at a tokamak, this shows a cross-section through one of our tokamaks, the D3D device in San Diego. This defines a few parameters. This is a cross-section showing the flux surfaces, the magnetic flux surfaces of the device. and I'll explain what I mean by that. It shows that we tend to operate now with not just circular plasma cross-section, but with elongated cross-sections. We have this configuration that's known as an X-point configuration. This is a form of the last closed flux surface here actually has a 0 point here. And we draw off the field lines down into the divertor region here. And I'll discuss what we use the divertor for tomorrow. Point I want to make here is that the plasma in the Tokamak, in any magnetic configuration, is its force-free I. It's in equilibrium, which is why we refer to this as the plasma equilibrium. It implies that you're both internal and external force balance. You can write that, you can express that as this simple equation, J cross B equals grad P. So basically the magnetic force counteracts the plasma pressure. It follows then that B dot grad P equals 0 and that J dot grad P equals 0. And what this means is that the pressure is constant on magnetic surfaces. And so these flux surfaces that I'm showing here are surfaces of constant pressure. It also shows that the current lines within magnetic surfaces, although the current is not constant, it's larger on the inside than the outside, but they lie within the magnetic surfaces. And we then define a colloidal magnetic flux function satisfying B dot grad phi equals 0, and it's this flux function that's shown here. It's a simple way of defining the geometry of the plasma, and it's got the nice property that the pressure is constant on this, and in fact a number of parameters are constant. Going a little further, we can then define this safety factor stability parameter more accurately as the rate at which the toroidal flux changes across the flux surfaces ratioed over the rate at which the colloidal flux changes. The absolute value of Q and its variation across the plasma radius are important to plasma stability, and I'll describe why tomorrow. You can also define the magnetic shear in terms of the Q in terms of this parameter, and the magnetic shear is the rate at which the twisting of the field lines changes as you go across the plasma. And this is an important property in terms of plasma confinement, in terms of protecting the plasma against the growth of instabilities. Another point I want to make here is that on the plasma pressure and the current profile are peaked on axis in a Tokamak plasma, quite distinctly peaked. And so this is the effect that this Q factor in the center of the plasma tends to be about unity, and at the plasma edge it's about 3. When we have this geometry in which we have a diverter configuration with an X point here, i.e. a 0 point in the edge of the plasma, it turns out to be difficult to define Q at the very edge. It actually goes to infinity because the colloidal field goes to 0 at this point. And so we tend to take a point which is what's called the 95% flux surface. So it's the flux surface that contains 95% of the colloidal field, which is very close to the edge of the plasma, and that we use to characterize the plasma. Another parameter which will come into discussion tomorrow is the plasma elongation, which is simply the ratio of the vertical minor axis against the horizontal minor axis. There are several parameters which then come out of this plasma equilibrium, which I'll be using in the discussion of the plasma physics tomorrow. The first of these is the normalized pressure, what we call the colloidal beta, and it's basically the kinetic pressure ratioed against an average of the colloidal magnetic pressure. And this is limited to basically to less than the aspect ratio by equilibrium considerations. The beta itself, which is the pressure normalized to the toroidal field pressure, is an important measure of plasma stability and of the efficient use of the field. And then there's one more equilibrium parameter called the internal inductance, which is basically a measure of how peaked this current profile is. And I showed you previously here the current profile is peaked, and just how peaked it is determines plasma stability parameters. And this value is typically in the region of 0.75 to 1.25. Let me turn now to some of the plasma physics considerations. There are a few basic parameters which characterize plasmas. The first of these is the Debye length, which is basically the characteristic length in the plasma at which the individual charges are shielded. In order for the Tokamak, for plasma in general to be treated as quasi-neutral, that is with no net electric fields, you have to satisfy the condition that n times lambda cubed is much greater than 1. Now in a Tokamak this is about 10 to the 8, so we're certainly well into that regime. A couple of other important parameters are the plasma frequency, which is the characteristic frequency of electrostatic oscillations in the plasma, given by this. It just depends on the square root of the density, basically. To give you an idea, at a density of 10 to the 20th, this turns out to be roughly 100 gigahertz. So these are wavelengths in the millimeter wave region. And then I'm sure a parameter you're very familiar with here at CERN is the Larmor radius. In a Tokamak, this is about 100 microns for electrons at 10 keV and 3 Tesla, and about 5 millimeters for protons at 10 keV and 3 Tesla. And obviously this has to be very much smaller than the scale length of the plasma in order to have good confinement. There's an important concept I need to introduce, which is associated with the toroidal geometry, and it's illustrated in this slide here. I mentioned before that the toroidal field in the plasma had a 1 over major radius dependence. So as you go from the outside of the plasma through the center to the inside wall of the plasma, the toroidal field increases as the major radius. And the effect of that is that as the charged particles then go around, swing around the plasma from the outside to the inside, they effectively meet a magnetic mirror. And this means that the magnetic moment of the particles gets wound up. It means that the parallel energy is transferred to perpendicular, the parallel velocity is translated to perpendicular velocity. And this means that a certain fraction of the particles never make it to the inside, but actually bounce back to the outside of the torus. And so you have what are called passing particles, which can make it all the way around, and you have a certain fraction of particles which can only get so far into the magnetic field mirror and then bounce back, and these are referred to as trapped. And the orbits they follow are shown here. They drift around the torus, they reach a certain point in the magnetic mirror, and they bounce back. And these elongated, what are referred to as banana orbits, these elongated banana orbits, then precess around the torus. This has an important consequence on some of the primary characteristics of the Tokamak plasma. It only happens, I should emphasize that it only happens when you get hot enough plasmas that the collisionalities or the collision frequencies are low enough. And what I mean by low enough is that the particles must be able to complete these bounces in the toroidal field before they collide with another particle and are scattered to another orbit. And the two principal consequences of that relate to the plasma resistivity. And the plasma resistivity is defined here. This is basically Ohm's law for magnetized plasma. E plus B cross B equals A to J, where H is the resistivity. One of the things resistivity depends on is the effective charge of the plasma. You have to sum up over all of all the ions, both the hydrogen ions and any impurity ions, and the effective charge is defined like this. It's a measure of how clean the plasma is. If you have a pure hydrogen plasma, Z effective is 1. We're never as lucky as that. Typically, Z effective, well, in ITER, we're aiming for Z effective around 1.6, 1.7. If you're careless, you can end up with Z effectives in the region of 2 to 4. Another important parameter is the Coulomb logarithm, which is a parameter which characterizes an average over electron-ion collisions. When you actually do the calculation, this calculation, and work out what the resistivity is, you find that it's given by this expression here. And the important thing I want to pull out here is that what it says is that the parallel plasma resistivity, that's the resistance, basically the resistance the current experiences, is inversely proportional to the electron temperature to 1.5. This tells you as the plasma gets hotter, the resistivity falls. And that has a couple of consequences. One is that it explains why the current is peaked on axis, because that's the hottest part of the plasma, it's the lowest resistance part, it's where it's easiest to drive current. The second thing it tells you is that as the plasma gets hotter, the total resistance of the plasma falls, so the ohmic loss, the ohmic heating of the plasma falls. And so this means that you can heat the plasma up to a certain extent by ohmic heating, but unfortunately the ohmic heating falls off too quickly, and it will never get you to ignition. So it can never get the plasmas that we work with to the range of 1 to a few keV. It doesn't get you to 10 keV. And so it means you have to find other ways of heating the plasma to ignition. Just to give you an example, at 1 keV, this resistivity is about 2 times 10 to the minus 8 ohm meters, i.e. it's about the resistivity of room temperature copper. Now this trapping effect that I described before has an important effect on the resistivity. Because some of the particles are trapped, it actually tends to increase the resistivity in the outer part of the plasma. So a graph of the resistivity across the jet tokamak from the central axis to the outside would look like this. But with the trapping effect, it actually looks like this. And so this means that the resistivity is typically about a factor of 2 on average higher than it otherwise would be. But it has another important effect, which is an effect that we want to exploit in building a power plant, which is known as the Bootstrap Current. And the way in which this arises is that there's a gradient. As I was describing, you have these trapped particles on the outside of the torus. There's actually a gradient in the density across the outside. So you have more closer to the axis than the outside. And so you get a type of friction between these different populations of trapped particles. You also get a friction with the passing particles. The net effect of this friction is there's a momentum transfer from the trapped particles to the passing particles. And what that does in the end is it distorts the electron distribution and velocity distribution function, and it actually generates an extra current in the plasma. This is what it's referred to as the Bootstrap current. You get a certain, if you like, you get a certain amount of current for free. You can get quite a lot of current for free if you're careful and if you set up the right sort of parameters. It turns out that the total free current, the total Bootstrap current, is given by this expression here. And so what this says is it depends on the inverse aspect ratio to the half times the poloidal beta. So this is a measure of the plasma pressure. This was an experiment in JT60, the Japanese tokamak, which was the same size as jet. This shows the Bootstrap current, measured Bootstrap current fraction as a function of the beta poloidal that they achieved. And they managed to set up high beta poloidal plasmas with beta poloidals close to their equilibrium limit, close to the aspect ratio limit, with Bootstrap current fractions of about 80%, in good agreement with the theory. This is an important concept because it's one of the ways that we can replace the transformer action in a tokamak and actually move the tokamak towards steady state operation. So I'll come back to the Bootstrap current tomorrow. This gives an overview of a simulated plasma pulse in ITER. There's just a few points I want to pull out of this. This is the time scale here the time scale here is of order 1600 seconds. Basically what we do is we ramp up the transformer current as shown in this trace here to its maximum current. We then discharge it through a set of resistors as shown here. The discharging of this transformer current causes the plasma current, causes an electrical breakdown and then causes the plasma current to ramp up. As you continue to discharge current through the transformer and then start to ramp it up in the opposite direction, you can continue to drive an electric field in the plasma and continue to drive the plasma current. So basically, at the end of the day, even with a lot of sophisticated and plasma physics, a tokamak is really just a large transformer. What we're trying to do, part of our research, is to move it away from being a transformer and to replacing this ohmic current drive with other forms of current drive. Because you need to replace the transformer action if you want to produce a tokamak that's capable of steady state operation that you would need in a power plant. So that's basically what I wanted to say about how a tokamak works and some of the basic physics concepts. I've described quite a lot of parameters here, but unfortunately the parameters that will come up again tomorrow when I start to discuss in more detail some of the cutting edge physics that we're doing in fusion research. And so I wanted to try and explain the jargon, explain the concepts in advance. Let me finish today's lecture just by briefly describing the ITER project and where we are. Basically, as I said before, ITER is a partnership of 7 major economies, the EU including Switzerland, which is associated with the European Fusion Program, China, India, Japan, the Russian Federation, South Korea, and the United States. So it represents more than half the world's population. The overall programmatic objective is to demonstrate the scientific and technological feasibility of fusion energy for peaceful purposes. And the principal goal is to design, construct, and operate a tokamak experiment at a scale which satisfies this objective. Basically, in scientific terms, ITER is designed to confine a deuterium-tritium plasma in which the alpha particle heating dominates all other forms of plasma heating. It's what we refer to as a burning plasma experiment. In our existing experiments, we're always heating the plasma from the outside, either with the ohmic heating or other heating forms. ITER should be the first experiment in which we're able to, the alpha particle heating is able to take over. In numerical terms, what we're trying to achieve is we want to achieve a significant fusion power amplification of at least 10 in long pulse. That means several 100-second operation. We want to achieve steady-state operation of a Tokamak at a somewhat less ambitious Q of around 5. And we want to explore the fusion power production regime, and if possible, move the fusion power amplification towards the region of controlled ignition, which is needed for a power plant. In technology terms, we aim to demonstrate the integrated operation of technologies for a fusion power plant. So that means things like very large-scale superconducting magnets, which make up the ITER magnet system. It means heating and current drive systems on the scale required for a reactor. We want to test specific components for a fusion power plant. That means things like the sorts of components you need to line the inside of the torus with to protect it from the plasma. And we want to test specific concepts for a tritium breeding module. As I mentioned earlier, one of the key issues for fusion development is that we're able to breed tritium in lithium inside the blankets. And we're going to test these concepts in ITER. So the ITER device looks like this. As I said, it's about the cryostats about 30 meters across, 30 meters high. The main elements of the device are shown here. Firstly, there's the central solenoid, which is an niobium tin magnet, niobium-3 tin magnet in the center of the device. The toroidal field coils are these structures in blue, which you can see better on the inside here. There's 18 of these, and again, niobium-3 tin magnets. There are then 6 colloidal field coils shown here, 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 and here, which are used to control and to shape the plasma, and these are niobium-titanium superconducting magnets. The cryostat is required, of course, because these are all superconducting magnets and operating at 4.2 Kelvin. The vacuum vessel is a double-walled structure shown here, made from stainless steel. Around the inside of the vacuum vessel are structures which are shielding blanket modules, and as I said earlier in the lecture, these are basically, in ITER, these are basically there to absorb neutrons and protect the magnets. In the bottom, we have the diverter, which is used to extract heat and particles from the plasma, and I'll describe its function in more detail tomorrow. We have a series also of copper internal coils, and we want to use, these are shown in green here, and we want to use these to help control some of the instabilities to which the plasma is subject. Thermal shield, part of the cryogenic system again. And finally, we have a set of external superconducting correction coils, again, niobium titanium superconductor, which we use to help correct out low amplitude error fields. And so these are the main elements making up the ITER Tokamak. So the status of the project, the ITER project, the concept of ITER actually started in the mid-1980s. It was launched at a meeting between Gorbachev and Reagan. I forget whether it was in Reykjavik or whether it was here in Geneva, in fact, the critical meeting, in which they were looking for a good scientific showpiece for collaboration between the US and the then Soviet Union. And so they launched the concept, and the project started with a conceptual design phase, went through an engineering design phase, and finally has now resulted in a construction project. The design for ITER was actually completed around the year 2001, but then the negotiations were a very long, drawn-out affair, in particular because the Europeans and the Japanese couldn't agree on where to site the project. It took a while to decide on Cadarache. But finally, in November 2006, the ITER agreement was signed in Paris. We started setting up the team in Cadarache in the course of 2006. In 2006, 7, and 8, we constructed a very extensive design review, and introduced some design changes. And in 2007, in parallel with that, we launched the construction activities. The ITER organization itself actually came into being in October 2007. This was a formal delay between the ITER agreement and the coming to being of the ITER organization. And after a number of years of negotiation and between the partners, further negotiation between the partners and the ITER organization, the ITER baseline defining the scope, schedule, and cost was finally approved by the ITER Council in July 2010. And so this gives us the formal basis for the construction of the project. It basically defines what we're going to build, how much it's going to cost, and how long it's going to take. the same time, in July 2010, a new Director General, Osamu Motojima, was appointed by the ITER Council. And in August of that year, building construction actually began on site. We've actually launched construction activities, industrial construction activities in the past, but the start of the construction on site was a big step forward for us. How much does ITER cost? Well, it's rather difficult to tell you how much ITER costs because we operate in the ITER system with this rather strange unit of accounting called an ITER unit of account. And 1,000 ITER units of account is roughly, was defined as $1 million US in 1989. And it's a simple way of accounting between the partners to exchange values between the partners. In real terms, this is roughly 1.5 million euros when inflation's properly accounted for. So the actual construction phase cost is 4,584 kilo units of account. So I won't convert that formally to a cost in euros because the actual cost to the partners of building the components for ITER is not necessarily directly related to this value. This is the conceptual value that the partners have agreed ITER will cost. What the components cost them to build may be rather different from that. We then have an operation phase budget of 188 kilo IUA per year. That will roughly, today's values, that's roughly equivalent to 300 million euros a year. And that means, but we won't actually get access to that until we start operation in 2019. There's then additional costs for the deactivation and decommissioning phase. The schedule of the project, this shows the main lines of construction associated with the construction activity. These are the lines that are closest to the critical path for the project. Down here you have the on-site buildings which are now underway, and these should become available for on-site assembly work in early 2015, and that's a critical point in the construction phase when we can actually start assembling the Tokamak in the Tokamak complex. In parallel with that, we build the sectors of the vacuum vessel. The vacuum vessel is made up of 9 very large sectors, which are being built by Europe and Korea. We build the central solenoid, which is being built by Japan and the US, and the toroidal field coils, which are being built by Japan and the EU. These all come together on the site. Starting in 2015, we assemble the Tokamak together. Should be closed up by about the beginning of 2019, and the idea is that first plasma should occur in November 2019. We then go through a sequence of operation upgrades, and our anticipation is that we will move to DT operation, that is fusion power production, in 2027. As I said, ITER is a collaboration, as well as the ITER Central Team in Cadarache. We have what are called domestic agencies in each of the partners, US Oak Ridge, Barcelona for Europe, Moscow for Russia, and so on. These are the organizations which will actually be responsible for interfacing with industry to build the components that will make up the ITER device. So all of the components I've showed you before in the ITER device, the coils, the vacuum vessel, the cryostat, will all be built under the responsibility of the domestic agencies and shipped to Cadarache, what's known as in-kind procurement. So the ITER organization only gets a limited amount of money. We're actually responsible only for 10% of that construction, of the actual procurement of components. 90% comes from the members. So the components will be shipped into Fos, which is near Marseille in Provence. It will then be shipped overland along this route to the Cadarache site, which is about 70 kilometers from Marseille. It's about 70 kilometers as the crow flies. It's about 100 kilometers due to this route. And this route is a very zigzag route because we have to avoid low bridges, we have to avoid small villages, and the local governments in France have actually spent quite a lot of money making this road fit for shipping the very large components which we'll need to bring into the ITER site. This is something the French are used to, of course, because in Toulouse, the Airbus is assembled in a similar way. That route is ready now, and the first test shipments will be later this year. The first real shipment should take place, I think, will take place next year. And this is what the construction site looks like now. If you come to Cadarache, you'll see that we're finally on the map. This shows the construction platform, and in the background here is the Durance Valley. We're just on the edge of the River Durance. As I said, it's about 70 kilometers from Marseille. In the background here is the CEA Cadarache site. This is, I think, the largest nuclear research site in Europe. There's about 14 fission reactors on this site. It also houses the French fusion experiment. We have some temporary headquarters here. So this is the construction platform. We had to move just over 2 million cubic meters of earth and rock to level this platform. And what's going on now here in the center is the excavation for the Tokamak complex itself. The Tokamak will be built into the ground. This is about 20 meters deep. We're going to build, the first thing we're going to do is to lay a large concrete slab, and on that we'll put a large series of shock absorbers, seismic isolation. It's actually an earthquake-prone area in Provence, and the Tokamak complex itself has to be seismically isolated. We're just about ready to pour the first concrete there. Over in the background here, this very long building here is the Ploidal Field Coil winding building. The Ploidal Field Coils are so large that they have to be wound on site. And this is a building that's about 250 meters long, and that'll be finished by the end of the year to start construction of the fabrication of the Ploidal Field Coils. And off on the right here is our new office block, which is just taking shape. To give you an idea of scale, this platform is about 1 kilometer long and about half a kilometer wide. This is